Hello everyone, my name is Min-Kyu Lee and I'm excited to present our research on AESOP, Auto-Encoded Supervision for Perceptual Image Super-Resolution, which was recently accepted at CVPR 2025. This work is in collaboration between Sang-hee Kyun, Woo-jin Jeon, and my advisor, Professor Jae-pil Ho. In this talk, I will cover what super resolution is and why we need it and how AI-based super resolution works, and the challenges in recent super resolution, and also important concept, the perception distortion trade-off, and finally, our proposed ESOP method and its advantages. By the end of this presentation, I hope that you'll have a clear understanding of why SR is a crucial area in computer vision and how ESOP improves existing super resolution models. I want to briefly introduce what CVPR is at the conference where this work has been accepted. CVPR stands for Conference on Computer Vision and Pattern Recognition. It's one of the most prestigious and competitive conferences in the field of computer vision and AI. And every year, CVPR brings together researchers from top universities, research institutes, and leading tech companies like Adobe, Amazon, Google, and Apple. And I'm very proud that our work was accepted to this conference, and it's an honor that I can have a presentation in this class. I would also like to introduce our research lab, the Visual Computing Lab, or in short, VCLab, which is a leading research group in computer vision and AI. Our lab focuses on various tasks in computer vision, including low-level image and video processing, deep learning for visual tasks, such as unsupervised representation learning and video understandings, and also in 3D vision and generative modeling, and more. Now let's begin by answering the question, what is super resolution? Super resolution, or simply SR, is a technique in computer vision that aims to enhance the resolution of a low resolution image. Let's go through a simple example of how super resolution works. First, we start with a low resolution input image on the left side. As you can see, it appears blurry and lacks detail. Next, we apply an AI-based super-resolution model represented by the small AI robot in the center. This model has been trained on large datasets of low-resolution and high-resolution image pairs, allowing it to estimate and restore missing details of the low-resolution image. Finally, we'll get a high-resolution output on the right side, which is much sharper with clear textures and more fine details. This particular example showcases the result of our proposed method, which outperforms traditional upscaling techniques by learning more accurate and fine details. To put in simple terms, imagine you have an old blurry photo. Instead of just stretching it, super resolution adds new details intelligently, making it look much more crisp and natural. Now that we understand the concept of super resolution, let's take a look at some visual examples of our method applied to times 4 upscaling. On this slide, you see several side-by-side comparisons of low resolution input images and their corresponding high resolution outputs generated using our proposed super resolution model. Each example demonstrates how our model effectively restores fine details, enhances textures, and improves overall sharpness compared to the blurry lower resolution input. So where do we actually use this technique? On the left side, we have an example from NVIDIA DLSS. Gaming requires high-quality graphics while maintaining smooth frame rates. However, rendering everything at native high resolution is computationally expensive. So DLSS solved this by using an AI-based super resolution model. It starts with a low resolution frame and intelligently upscales it to look like a high resolution image. This reduces the GPU workload while delivering better visual and improved performance. We also have medical imaging examples such as MRI and CT scans. And also, if you have ever used a flagship smartphone like an iPhone or a Samsung Galaxy, you've already experienced AI-powered super resolution in action. Now that we've discussed why super resolution is important, let's look at how AI-based super resolution actually works. Super resolution models are trained using a process called supervised learning, where we provide a model with pairs of low resolution and high resolution image pairs. On this slide, I will walk you through the basic training process for AI-based super resolution models. First, we take low resolution image as input, shown on the left side. Then this image passes into a SR network, which is typically either a convolutional neural net, simply CNN, or a transform-based one. The goal of this network is to estimate the corresponding high-resolution image, which we call the SR, or the output. Once the model generates an SR output, we compare it to the ground truth high-resolution image HR, and we measure how accurately the generated SR image is. And we use mostly a simple loss function, in this case, the per pixel L1 loss. One of the biggest issues in super resolution is that it's an outpost problem, which means that we can't determine a unique solution. Since the AI model doesn't know which version is the ground truth image, it often generates a result that averages among all possible solutions, which tends to be blurry. Notably, this happens for any per pixel loss, and throughout this presentation, I will use the term LPix to represent any per pixel L1 or L2 loss and other variants of them. Jumping deeper into details, this diagram provides graphical illustration of the overall super resolution system and highlights one of its key challenges. First, let's discuss the role of LPix, the pixel-wise loss function. LPix is essentially a form of maximum likelihood estimation, simply MLE, which means it optimizes the probability distribution over the prediction space to find the point that maximizes the expected likelihood. However, this optimization process does not select a single plausible HR solution. Instead, it converges to an average result, which is why the final output often becomes blurry. This is one of the fundamental problems in traditional super resolution approaches. And then the question is, how can we move away from these blurry results and instead train models that generate sharp and perceptually convincing images? For now, the common solution to the blurring phenomenon is to introduce perceptual loss, LVGG, and the adversarial loss, LGAN, to enhance realism and fine details. I won't go into much details about these loss functions, but what you need to remember is that these additional losses significantly improve visual quality and are widely used in modern super resolution models, but often hinder fidelity convergence. Important point here is that is this a free lunch? Can we get sharper and more realistic images without any drawbacks? The answer is unfortunately no here. And in fact, there is a fundamental theoretical limitation to super resolution models, which we call the perception-distortion trade-off. Let's dive deeper into what perception-distortion trade-off is. Let's first look at the left side of the slide, which provides a conceptual illustration of this problem. The yellow and gray circles represent different possible high-resolution images that could correspond to a given low-resolution input. The blue dot labeled as fidelity SR image represents an output optimized for minimum per pixel error. And this approach produces blurry images because it's the average among all possible solutions, which we have discussed earlier. The pink dot labeled as perceptual SR image represents an SR result optimized for realism using additional perceptual-oriented losses. And this version introduces much more natural textures and high-frequency details, but has additional error highlighted by the red arrow, because the generated high-frequency textures are different from the actual high-resolution image, which must lead to lower fidelity scores. And now let's look at the perception distortion trade-off curve on the right side. This curve shows the fundamental relationship between perception, which indicates realism, and distortion, which indicates per pixel error in super-resolution models. We have a blue curve here, which indicates the upper bound of an ideal super-resolution model. And as you can see, we have a clear trade-off relationship where when we aim for improved perception, we must lose fidelity and vice versa. Theoretically, no method cannot go under this curve. And when we say that a model performs better than the other, we mean that it's closer to the blue curve. In this work, we're also aiming to go closer to this blue curve, not going across this line. Now, given the concept of the perception-distortion trade-off, we'll discuss if our approaches are optimal. They either multiply a small coefficient to LPICs or apply low-pass filters before them. This design is to reduce the impact of high-frequency components from being penalized, which is a fundamental cause of the blurring phenomena. However, later I'll show that these certain conventions both lose more reconstruction guidance than required. That means they lead to higher distortion than required for their given perceptual level, as shown in the graph on the right side. From now on, I'll introduce you our method and some concept we have defined for this. Here, we first define the term fidelity bias and the perceptual variance. The perceptual variance is the random factor when we perform image super-resolution and leads to blur when removed. The fidelity bias is the average solution of the super-resolution process, or else the fidelity SR version of an SR image. Accordingly, we could define the ground truth fidelity bias, which is the optimal fidelity point, and the fidelity bias induced error, which is the distance between our predicted fidelity bias and the optimal fidelity point. Looking at the left side of the diagram, we see that perceptual super-resolution images contain a range of plausible high-resolution outputs. This variance represents natural texture differences that should not be eliminated and has some inherent randomness. If we over-optimize for fidelity and remove this perceptual variance, our model will collapse into a single average prediction, leading to blurry results, the very problem we wanted to avoid. Now, given a certain level of perceptual quality, we should aim to minimize the fidelity bias-induced error to improve fidelity. In other words, we want to simply align the blue and gray circles. Importantly, minimizing this error does not affect perceptual variance. It only provides improved fidelity without harming realism. This means that we can reduce per pixel error while maintaining perceptual quality if we only minimize fidelity bias-induced error. From now on, we'll refer to this perceptual variance-induced error as the variance effect VE and the fidelity bias-induced error, which is the systematic effect, as SE. Overall, we are claiming that we must preserve VE while minimize SE. Thus, we'll show that current approaches are failing to do this, and we will accordingly propose a method to achieve preserving VE and minimizing SE.
Here, I don't want to go into the details about complicated math, but note that LPICs is basically MLE as in the upper right corner, and this can be divided into two terms, which is exactly the terms we have defined in the previous slide, the SE term and the VE term. This means that LPICs can be understood as minimizing both SE and VE. Since we have discussed that VE reduction leads to blur, we have now narrowed down which factor of LPIC specifically leads to blur. So visually, the overall optimization procedure would look like this. The prediction space, the blue circle, will be aligned towards the true solution space, a gray circle. But also, it will degenerate to the sole average point, leading to blurry results. Accordingly, we can think about a straightforward solution, which I will introduce you in the next slide. Instead of minimizing both SE and VE, we could design a loss function where only SE is minimized. By doing this, we could improve fidelity scores for a given level of perception level without leading to additional blur for this guidance. Visually, instead of both aligning and degenerating the prediction space, we propose only to align the centroids of each space, as in the right side of the figure. This would be a simple overview of our method, where we replace LPIX, the per pixel L1 loss or L2 loss, fundamentally reducing both SE and VE into a loss function that only reduces SE, the systematic effect. Then we apply this with other perceptual quality-oriented losses together, which will now lead to the highest perceptual quality the perceptual losses can provide, while achieving the highest fidelity scores for that specific given level of perception. So what would be nice if you could compare these left and right figures, and about the SE plus VE, which indicates LPIX, and only SE, which stands for our proposed loss function. Now that we understand the importance of separating fidelity biases and perceptual variance, the next question would be, how can we estimate the fidelity bias of a given image? Since fidelity bias is the systematic deviation that causes error in traditional SR models, we need a way to quantify this and somehow minimize it. To achieve this, we introduce a differentiable operator psi, which acts as a fidelity bias estimator. The role of psi is to take an image as input and estimate its fidelity bias. Instead of using the conventional LPIX loss, which we know leads to blurring due to pixel-wise averaging, we propose a new approach. We use the fidelity bias estimator psi to compute a new loss function, which directly measures and minimizes SE. By training our SR model to reduce the systematic error rather than per pixel differences, we can maintain sharp perceptual details, improve fidelity without sacrificing perceptual quality, and also avoid the blurring effect of traditional pixel-wise losses. This means that our method effectively substitutes LPIX with a loss function that directly targets fidelity biases, leading to a better balance between realism and accuracy. Here, when you recap the definitions, each element in the definition of SE corresponds to the expectation of the higher resolution image given the lower resolution image, and the average of our solution likewise, where the support of the distribution, each y and y hat, is a distribution conditioned by the downsample version of each. Accordingly, this simplifies into training an autoencoder that first encodes a high-resolution image into a bottleneck representation, which effectively estimates the downsampled version of the high-resolution image. Second, it reconstructs the original high-resolution image given only the encoded representation. The key insight here is that the bottleneck feature is treated as an independent random variable from the decoder's perspective. This ensures that the learned feature space correctly captures the expected fidelity bias without overfitting to specific HR instances. Now, overall, finally, our method can be summarized as first, pre-training an autoencoder as in the left side of this slide, and then substituting the original LPIX with the proposed autoencoded loss. This enables us to only reduce SE while preserve VE, which was impossible under conventional per pixel reconstruction loss, indicated as LPIX. Now, when we put everything together with other loss functions, we get the following figure. This slide compares the impact of traditional loss functions versus our proposed approach when using perceptual super-resolution tasks. The key difference here lies in how fidelity bias and perceptual variance are handled. In the baseline method, both fidelity bias-induced error and perceptual variances are reduced. Thus, the prediction space are aligned, but are also degenerated, leading to blurry results. Meanwhile, in the proposed method, the fidelity bias is aligned with the one from the ground truth space, while perceptual variance is preserved. Additionally, an important point here is that we do not apply a small scaling factor for the reconstruction loss. This type of small lambda for the reconstruction loss was to reduce the impact of VE reduction, thereby avoid blurring. However, this also reduces unintentionally the SE reduction factor. This means that the network cannot receive sufficient reconstruction guidance, and since the adversarial loss works in a test-blind manner, it generates realistic textures, but are not guaranteed to adhere to the input image. Accordingly, the adversarial loss with reduced SE reduction will potentially lead the super-resolution network to generate images that does not precisely align with the input image, or also may lead to unintended visual artifacts. Meanwhile, since we do not multiply a small coefficient, we can get a much more stronger reconstruction guidance while also avoid blurring. Here we provide some intuitive figures that compares our proposed AESOP loss against conventional per pixel level loss. As can be seen, since we have isolated SE and VE and only penalized based on SE, the loss scale exhibited by our proposed loss is smaller compared to the original LPIX loss. However, when the coefficients are applied, our loss shows significantly higher level of scale, indicating that we provide much stronger reconstruction guidance as discussed in the prior slides. Below, we also have some visual examples of the loss maps of each losses. And LPIX blindly penalizes all factors of the image, even including the very high frequency details that cannot be regressed by super-resolution models and would lead to blurring if penalized. Accordingly, this leads to obvious blurring as shown in B of this figure. Meanwhile, the proposed AESOP loss only tackles the factor that can be regressed, and these do not include the very high frequency details with randomness that would lead to blur if reduced, but does include the overall structure of the image, which acts as an important reconstruction guidance and does not induce blur. Accordingly, we can generate images that both adhere better to the original LR image and also has significant improvement in the visual quality. Here we compare the performance of a super-resolution model trained with our loss and the conventional per pixel LPIX loss. AE-PSNR and LR-PSNR are each PSNR scores after the autoencoder and after downsampling. AE-PSNR directly indicates the level of fidelity bias-induced error, or simply SE, and higher AE-PSNR indicates that we have well aligned the prediction space and the solution space. Meanwhile, LR-PSNR indicates how well our image adheres to the original input image, and we show significant improvement in both metrics. We believe that this is due to the significantly stronger level of reconstruction guidance we have provided, since we do not multiply a small coefficient to the reconstruction loss factor. Here we would like to discuss about the difference against low-pass filtering in our method. At the beginning of the presentation, I've told you that someone might use low-pass filtering in order to avoid blurring. This is since the blurring is induced when high-frequency factors are penalized. And this is indeed true, and low-pass filtering may help resolve this. However, the figure below shows that fidelity biases, which we are mainly penalizing, are not solely low-frequency factors. They include specific high-frequency components such as structural edges, importantly, which are factors that can be regressed. Accordingly, our proposed AESOP loss provides additional reconstruction guidance on specific high-frequency factors that do not induce blur, but are important as a reconstruction guidance but traditional low-pass filtering cannot do this. Thus, when we apply low-pass filtering instead of our autoencoder, it shows substantial performance drop over all benchmark datasets. Here we have the overall benchmark table comparing prior state-of-the-art method with both the RRDB backbone, which is a CNN-based super-resolution architecture, and a SwinIR backbone, which is a Swin transform-based architecture. As can be seen, we achieved state-of-the-art performance in all datasets over all metrics. I won't go into details about each baseline methods or evaluation metrics here. You just have to know that despite perceptual quality metrics and distortion metrics are often known to have trade-off relationships, and it is often very hard to improve both of them. By simply introducing a pre-trained autoencoder enables this significant performance improvement. In the prior slide, I've shown that our method leads to improvement in both perceptual metrics and also in distortion metrics. Now we'll show them in a graph. I recapped that earlier slides where I have introduced about the perception-distortion trade-off curve. We say that a method performs better if it's closer to the left bottom corner. And as can be seen, we significantly outperform baseline methods, including the most recent state-of-the-art method, LDL. We also have more visualization for the perception distortion trade-off curve and comparison with other recent baselines in the supplementary materials. So we highly suggest you to have a look over them. I won't go into details for that since we have limited time here. We finally will show some visual results here. Since we do not reduce VE, we can see significantly improved perceptual quality, for example, in the fine-grained hair textures. Also, since we do not multiply small coefficient to the reconstruction loss term, we provide a much more stronger reconstruction guidance overall. Thus, we can generate images with much more less visual artifacts that are induced by adversarial training. We have some more additional information here, but I won't go into details right now. I have some more detailed parts about our work that I would like to introduce, but due to very limited time, I would just briefly highlight the key points, and I encourage you to take a look on your own if you're interested in more details. Here we have some more details about the equations, and additional details and some intuitions for them. We also have some high-level conceptual illustration about how AESOP works, and some more high-level conceptual illustration about the perception distortion trade-off curve, and comparison between AESOP and the conventional per pixel loss LPICs. And finally, we have some simple ablation results. I'd like to thank you all for your time and attention today. I hope this talk has given you a clear understanding of super-resolution, the perception distortion trade-off, and how our method addresses these challenges. If you're interested in more details and have any questions, feel free to check out our paper or reach out to me via the email address below. Thank you.